Supermassive black holes are the most massive, gravitationally dominant objects in the universe. Matter falling toward the center is violently shredded and superheated, generating enough radiation to outshine every star in a galaxy combined. But according to the established laws of physics, there is a hard mathematical limit to how fast they can actually consume that matter. This diagram illustrates the Eddington limit. To feed steadily, a black hole's inward gravity must perfectly balance the outward radiation pressure generated by the blazing hot matter. If the accretion rate spikes, outward radiation overpowers gravity, violently blowing the surrounding food source away. A black hole that gorges itself will starve itself. This makes the existence of massive black holes in the very early universe a physical paradox. They shouldn't have had enough time to grow this large. To understand how these early giants reached such massive sizes, astronomers pointed the James Webb Space Telescope's infrared sensors toward the dawn of time. They targeted an early universe black hole named LID 568, observed as it existed just 1.5 billion years after the Big Bang. This scatter plot compares black hole mass on the bottom axis to bolometric luminosity on the left. The red star marks LID 568. It is pulling in matter at a rate 40 times higher than the theoretical Eddington limit. This creates a secondary problem. Active black holes shoot out massive jets of energy that heat up the gas in their host galaxy. That intense heat should prevent gas from condensing and falling inward, effectively cutting off the black hole's fuel supply. JWST data proves these early monsters feast at rule-breaking rates. The math shows the growth is happening. Now we have to determine how they sustain this appetite without blowing all their food away. To find the physical mechanism, astronomers shifted their focus to a much closer target, a giant elliptical galaxy called NGC 4696, located in the Centaurus cluster. Webb mapped the exact feeding zone of this galaxy's central supermassive black hole with a resolution of just 30 light-years, a tiny slice of a galaxy that spans hundreds of thousands of light-years. Deep inside the black hole's gravitational influence, they found an 800 light-year-wide accretion disk of cosmic fuel, racing around the center at 600 kilometers per second. This high-density mapping provides the first look at the physical connection between the outer galaxy and the black hole's inner reservoir. The solution involves the very energy jets that were thought to starve the black hole. The cycle starts when these jets heat up the surrounding gas and push it outward into the wider galaxy. In this flow model, expelled heated gas moves outward, cools, and slows down. This unstable gas condenses into long, narrow filaments, stretching thousands of light-years. Guided by magnetic fields, these dense filaments arc backward, funneled directly toward the galactic center. Webb captured these cooling filaments physically merging with that 800 light-year-wide accretion disk, providing the missing link in the feeding process. Supermassive black holes survive because they recycle their own exhausted energy. The energy they blast outward creates the exact conditions necessary to condense gas and pull it back in for a continuous, self-feeding loop. This recycling mechanism changes our definition of a black hole. It is less of an isolated vacuum and more of a self-sustaining engine. This cycle dictates the rate of star formation across the galaxy. By regulating how much gas is heated and then returned, the black hole throttles the emergence of new star clusters. This feedback loop doesn't just feed the black hole, it drives the evolution of the host galaxy over billions of years. By capturing the physical connection between the jets and the incoming gas, astronomers have identified a self-regulating cycle that explains how black holes and galaxies evolve together as a single connected system.